It's my pleasure to introduce our speaker, Daniel Brooks. He's Senior Visiting Fellow at the Hungarian Institute of Advanced Studies, Község in Hungary. So Daniel is an evolutionary biologist and parasitologist, and I read here he was the coordinator of all parasites, inventory of all parasites in Costa Rica. He's done a lot of conservation work. He's very interested in that link between climate change and also the emerging pathogens, the topic for tonight, for this afternoon. And of course, he tells me he started off in America, then he went to Canada, and is now in Hungary. So that's an interesting journey in search of whatever. So Daniel, please address us. Thank you.
Thank you very much. Thank you very much for the invitation, Jan and everybody. My first time in Singapore, and in fact only my second time anywhere in Asia. All of my research life has been spent in Central America and South America. But hopefully some of what I have to say may be relevant in some way to your particular situation. So I want to start with, instead of trying to end on a high note, we'll try to start on a high note.
Fasten your seatbelts. It's going to be a bumpy night.
Okay, so I'm going to talk about climate change and disease, emerging disease. And I'm a scientist. I'm a muddy boots biologist, we're sometimes called, a field biologist, parasitologist, and evolutionary biologist by training. And so some of the things I say may sound to non-scientists as if they're not very nuanced and not very well categorized or something like that, but that's just kind of the style. And it's not, if I offend anybody, it's completely unintentional, but I have been known to do that. The first thing, and this is a slide that is actually more important in my home country, the United States, where, in fact, climate change does not exist. It's the only part of the world where climate change doesn't exist. And I need to tell people that, in fact, climate change not only does exist, but it doesn't discriminate against or for anybody. So it is literally beyond belief. There is no human belief system that is spared the effects of climate change. It's sort of an equal opportunity phenomenon. One of the things that we need to do is to put what I'm going to say in a context. And part of that context has to do with the evolution of temperature profiles and the evolution of fluctuations in temperature profiles during the last million years or so. So the last million years of human history, the last million years of Earth history. And as you see from this diagram, most of what has happened in the last 800,000 years or so has been characterized by, last 80,000 years or so, has been characterized by a lot of fairly large amplitude fluctuations in climate, and not so much nice long periods of stability, except, except right here. It's about 10,000 years ago. Not only did we leave the last ice age, but we entered into a period of what turns out to be really unusual, highly unusual climate stability. And it turns out that that's the period of time when human civilization emerges. And because we don't know for certain that this was a requirement for human civilization to emerge. But we do know that civilization emerged during a period of unusual climate stability. And this affected a lot of the development of our scientific beliefs. It was one of the things that led people like Isaac Newton to mistakenly believe that the world operated as a clockwork mechanism and that the world was deterministic and predictable and we could control the laws of nature so that we could cheat on them to our own benefit and all these nice sort of Enlightenment aspirations of the physics community. Biology emerged rather late as a profession. So, oh no, Jiminy Christmas. That's really bizarre. Okay, so anyway, so we go back here. Now this is basically where human civilization emerges. And we go along for a very long period of time with not a whole lot going on. Even the little mini ice age was not such a big deal relative to what had happened before. And now, of course, we're beginning to see some major changes in climate. The question of what's causing that, in some senses, is irrelevant. Okay, I mean, the issue of whether we're causing it, we caused it, blah, 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 that's important in some context. But for what I'm saying, it doesn't matter what's causing it. What's important is that it's a real phenomenon that's happening, and we need to explore some of the consequences of that. Now, for millennials, there is a new set of the four horsemen of the apocalypse. Okay, it's slightly different from the traditional one, but these are basically geohazards, food supply, war, and disease. And I'm just going to talk about one of them. But of course, the four horsemen all ride together. So I'm not suggesting that these are, in reality, independent variables. But my mind is not capable of handling more than one of them at a time, and even then, just one part of one of those. So the first thing we have to remember, though, or understand is that the phenomenon of emerging diseases is not as the popular narrative would have you believe. That is, the emerging disease crisis is not a phenomenon of a relatively small number of viruses killing a small number of people in tropical countries. The scope of the emerging disease crisis is that it covers all diseases affecting humans and every species that humans depend on for their survival and socioeconomic development. And it covers diseases that we've never seen before and old favorites making a return engagement. And we'll see a couple of those at some point. Yes, I see. It also turns out that EIDs, as emerging diseases, come from everywhere. We get them in our water, food, air, casual contact. Someone sneezes on you in an airport. Someone coughs sitting in the seat next to you in the airplane. We get them from sex. That's how Zika became established in the United States, even though the CDC says it's not in the United States yet. We get them from wildlife. We get them from pets. We get them from anything that feeds on us or bites us or feeds on any of the animals and plants that we depend on. They show up in rural, urban, and wildland settings, tropical and temperate zones, and in developed and developing countries. So literally, there is no part of the planet that's safe from emerging diseases. The EID crisis is a national security issue for every country because it affects water security, food security, public health security, sociocultural security, and economic security. And something is very wrong. And I say that from a scientific perspective because new diseases are showing up almost daily. And it's happening much faster than the science that I learned as a graduate student would lead us to believe it could happen. We're also hemorrhaging money and resources. It's really clear that we're spending a lot more money on emerging diseases than we have. when organizations like the World Health Organization and the CDC actually call press conferences and say, we've run out of money and we've run out of resources and we can't get a handle on this, and it's a relatively confined disease outbreak that dies out spontaneously within 2 months, then there's a problem, a huge problem. And one of the reasons that we're having a problem is because healthcare professionals, medical and veterinary, are ruled by the principle of do no harm. And this is actually something that Hippocrates suggested. So once again, we blame the old Greeks about something. Do no harm in this context means wait until there's a crisis and then try to do something about it. Now that's fine if there is no climate change and there are no emerging diseases. In other words, as long as the world is completely predictable, we know what the diseases are, we know what they're going to be, they're not going to change, then do no harm is fine because you know what you're dealing with, and it's a very small number of entities. But waiting until the crisis has happened to deal with it is not economically sustainable, and ignoring the problem will not make it disappear. So the CDC saying that Zika is not a problem in the United States isn't going to change the reality that Zika is, along with dengue fever and chikungunya and West Nile virus, are filoviruses that are all established in the United States. So we have this paradox, which is, with all of our scientific knowledge and experience, all that expertise, why is there an emerging disease crisis? And even worse, why are we losing the battle? What's wrong with us? And by us, I mean the scientific community, because it's our responsibility to provide the best possible science for the practitioners who try to implement some of the ways of dealing with disease. And the reason is that our scientific beliefs, what I was taught as a graduate student about the evolutionary nature of pathogen host systems, is not correct. It does not accord with what we're seeing. Now, I'm not going to ask you to read this, but there are 5 statements in this, and this is a statement about emerging infectious diseases. It's the definition of emerging infectious disease by the European Bioinformatics Institute. And what I'm going to say is there are 5 statements here, and only 2 of them are completely false, but none of them are completely true. And there's a 6th larger statement here, which says that emerging diseases are viruses. So this reinforces that narrative that the emerging disease crisis is just about a few viruses, and that something really, really special and strange has to happen before a disease can jump into a new host and cause an emerging disease. But if that was true, then there wouldn't be a disease, an emerging disease crisis. It wouldn't be happening that often. And we know that we're lying to ourselves about this, because here's another European Union disease website, which points out that despite the narrative that Zika is a virus of human beings that's transmitted by mosquitoes, we know that Zika is circulating in a whole bunch of non-humans all over the place. We also know that Zika is transmitted primarily sexually. It can be transmitted by mosquitoes, but it became established in the United States several months before it was warm enough for mosquitoes to emerge. Appropriate mosquitoes vectors do occur in the United States. In fact, they occur all the way to southern Canada. But Zika became established in the United States. Zika became understood as an analog of rubella, that is, a fairly mild disease in adults that causes devastating developmental effects in fetuses as a result of sexual transmission. And the Brazilians have understood this for 2 years. And I know that because I've been in Brazil off and on for the last 3 years, watching this happen. So the current paradigm, the current coevolutionary paradigm says that ecologically specialized pathogens, strongly co-adapted to their hosts, so we call mutual adaptation or reciprocal adaptation, should not be able to change allegiances easily. In other words, the cost or a byproduct of being really, really closely adapted to your host is that you don't have many other options. But there is what's now called the Parasite Paradox, which is that we do know that pathogens are ecological specialists. We know that they're tightly co-adapted to their current hosts, but we also know that under conditions of changing environments, that they jump hosts readily all the time. The inventory that I ran in Costa Rica for 10 years and a parallel set of inventories that a colleague of mine was running in the Arctic during the same period of time showed us that consistently the species of parasites that we were finding were either parasites nobody knew about, and that's a problem that I'll come back to, or they were parasites that we had already known about, but they were never in the right host. They were always in a different host. So we were always being surprised at finding this, what is this parasite doing here? What is this parasite doing there? And now we know from what are called phylogenetic studies, that is deep history evolutionary studies, we know that pathogens switching hosts like this, that is producing emerging diseases, has happened a lot. What's happening today, regardless of the trigger for it, what's happening today is a repeat of an evolutionary pattern that we see going back all the way back to the Triassic. So we need a new paradigm, and fortunately, we actually have one. It's called the Stockholm paradigm, and that's named in honor of a group at Stockholm University who are specialists in the coevolution of insect and plant systems, but it turns out that host parasite systems, host vertebrate pathogen systems, show exactly the same patterns as the insect plant systems. And the basic dynamic module of the Stockholm paradigm is that specialized pathogens are able to add new hosts by a phenomenon that's called ecological fitting. New genetic information is not required to jump hosts. The ability to move into hosts through ecological fitting, I'll explain that in a second, allows pathogens to generalize themselves ecologically. It moves them out into new hosts, into new geographical areas, which opens up a lot of new space for genetic exploration and for colonizing new habitats. Once a parasite or any kind of pathogen has explored this new space, then in particular isolated parts of that new space, you have the option or the possibility of localized co-adaptation phenomena to occur, which then produces new sets of specialists. And repeated episodes of that module is what creates pathogen diversification. And since more than 50% of the species on this planet are parasites of some sort or another, this is obviously a really effective way for evolution to occur. Ecological fitting is a term that draws our attention to the fact that the occurrence of a pathogen in a given host is the result of both capacity and opportunity. And no matter how specialized a local association between a host and a pathogen may be, there are always possibilities of other hosts in other areas that are susceptible but have not been exposed to that pathogen as a result of things as simple as just geographic distance, geographic isolation, or ecological trophic isolation. So the capacity for expanding into new hosts is always there, waiting for something to create new opportunities. And those new opportunities do not initially have to involve the evolution of any new genetic information at all. The deep history evolutionary studies that we've done indicate that, as I've said before, in the past there have been a lot of episodes of parasites jumping and pathogens jumping into new hosts. But it turns out that that's not randomly sprinkled throughout evolutionary history. There are bursts or episodes of emergence of pathogens in new hosts. And those have always been correlated. For every study we've been able to do, those bursts of host switching, those bursts of changes of allegiance, are always associated with episodes of regional or global climate change. So it appears that it's climate change that triggers new opportunities simply by allowing things to move around. If you live in an area that has been wet and it becomes dry, you will move away. If you're in an area that's dry and it becomes wet, you'll move away. And as you begin to move around, tracking the environment that you normally live in, which now doesn't exist where you were originally, as you move around, that's all it takes. You're going to come into contact with hosts that are susceptible but have never been exposed before. Now, the good news about this is that this evolutionary dynamic shows how easily evolution can generate diversity following climate change events, including mass extinctions. And that's why we see this picture that the paleontologists have known about for a very long time. That following extinction events, there is not only a renewal of biodiversity, it's not the same species that come back, but there is evolutionary diversification following extinctions, but it also turns out that there's a very strong correlation between the speed and the extent of diversification and how severe the extinction event was. The more severe the extinction event, the faster new biodiversity evolves afterwards. Yikes. Okay, now the bad news is that one of the manifestations of things moving around as a result of climate change is all these pathogens moving into new hosts. So it turns out that one of the strange things about the emerging disease crisis for an evolutionary biologist is this is really good evidence for us that the biosphere is beginning to adapt to climate change. The emerging disease crisis is a manifestation of evolutionary biology, evolutionary systems' ability to cope with major environmental insults. But that means it's time for us to really pay attention because it means that the biosphere has started to cope with climate change without asking our permission and without waiting for us to participate. From the standpoint of the evolutionary system of life on this planet, we're just a species. And if we make it, that's fine. If we don't, that's fine too. So we're the ones who have to decide whether or not we're going to participate in what the biosphere has already started to do. Now, human beings, as we exist today, are characterized by two things that mimic the Stockholm paradigm dynamic, okay, in the sense of human beings moving around the planet and human beings moving things around the planet. Now, one is overpopulation, the other is globalization. So we move ourselves all over the planet, coming into contact with pathogens we've never seen before. We move plants and animals around the planet, bringing their pathogens with them into new places, bringing plants and animals into places where they meet all kinds of pathogens they've never seen before. So humanity is actually creating, we're large enough and we're widely distributed enough, and we have the technological capabilities now to be able to mimic what climate change is already doing. And we get to make it go faster. Emerging diseases are most often due to the expression of pre-existing capacities. That is, you don't need new genetic information to jump into a new host. And that includes rare variants, okay? So in the genetic variation distribution of a species, out here in the tails of the distribution, where the frequencies of genetic variants are so low that natural selection doesn't see them, that's where all the interesting stuff is. In terms of evolutionary diversification, that's where the interesting stuff is. Unfortunately, that's where all the pathogenic strains are too. That's one of the reasons we miss them, because it takes really intensive sampling to get those rare genotypes. Taking advantage of opportunities allowed by pre-existing genetic variation is what allows pathogens to get into new hosts, where they can then establish new coevolutionary relationships with the new hosts, which set the stage for the emergence of yet more capabilities. And that's, together, this is what allows pathogens to emerge into new hosts rapidly, but also allows pathogens to persist for very, very long periods of time. They're extremely good at, not only are they extremely good at finding us, they're really good at surviving. So now that we know what this has happened, why this is happening, okay, why is there a crisis? What are there some things, some problematical things about what we've been doing that this perspective explains? Well, one of the things it explains is why this notion of co-extinction is not going to help us. So there's a relatively new idea that hosts and parasites are tightly tied together. The parasites can't jump because they're so tightly co-adapted with their host. So if the host goes extinct, it takes the parasite with it, and one less pathogen for us to worry about. Unfortunately, that's not what happens. For example, my friend Eric Hoberg documented 25 years ago, he documented tapeworms living in alcid birds in the Arctic that are 20 million years older than the birds they live in today. These things were originally tapeworms in marine archosaurs that are now extinct. They went extinct at what we call the KT boundary. When the asteroid hit the Yucatan, those hosts went extinct. Parasites didn't. Parasites just moved into something new. And they're still living there. So co-extinction isn't going to work because of ecological fitting. Extinctions in general are not going to work. All that's going to happen if we have a lot of vertebrates going extinct is that the ones that survive are going to be the ones that can move around the most, and the ones that have the largest population sizes, they're the ones who are going to load up on the parasites and the pathogens. So the species of hosts that survive mass extinctions the best are going to be really, really good sources of diseases. They're going to be really good reservoirs. So extinction's just not going to help us at all. Biocontrol. Biocontrol is one of these. What is the definition? What do we call it when you keep doing the same thing over and over again expecting a different result? Biocontrol. Biocontrol never works. And it never works because we always look at the biocontrol agent in its natural environment and say, oh, look, it only attacks that host. We never ask if there's something in the new environment where we're going to introduce it that it might like better. So that's how we end up with something like, we got a pest insect on imported orange trees in Hawaii, but where the orange trees came from, there's a parasitoid wasp that attacks that pest insect, so we'll import it to control the pest insect. And then a year later we go, wait a minute, that parasitoid is attacking other insects, native insects, that turn out to be essential pollinators of native plants in Hawaii that we don't want to go extinct. And we do this over and over and over again. Well, this is why biocontrol is so problematical. Okay, why are these host switches, if we're saying that these are pathogens just moving into hosts that are susceptible, why does that result in disease? Well, it turns out it's because natural selection cannot operate on things that have not happened. So even though the new hosts are susceptible genetically, they've never been exposed to those pathogens before, so there's never been selection for resistance and tolerance. And so there's always the same pattern. There is emergence, there is acute disease. The acute disease dies back. The pathogen becomes a chronic part of the ecosystem, a chronic disease. It's no longer an acute disease. Occasionally it'll break out. But the important thing is that the acute phase is this strong selection for resistance. The non-resistant members of the population are knocked out. This is exactly what happened with West Nile virus in North America. And this works really well. And natural selection is a very powerful process. But the important thing is that the pathogen, even after exerting that strong selection for resistance on the host population, the pathogen doesn't just disappear. It stays there as part of what we call pathogen pollution. It never goes away. And so even though it may not be causing a severe disease outbreak the next year or the next decade or the next 20 years, it's there, and it takes some amount of human resources and material resources to pay attention to it. And that's why we call this the death by 1,000 cuts. You don't need the Andromeda strain to destroy the economic capabilities of healthcare delivery systems. You just need a lot of these little things happening all the time. And eventually, there will be so many little brush fires that you can't put them all out because they never disappear. Now, here's the interesting thing. I've just told you we've got this big problem, we're doing everything wrong, blah, 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 right? So you go, okay, so we can't continue to do what we're doing. The problem is we cannot stop what we're doing. We can't stop this because humanity is now living in a constructed niche, a heavily constructed niche, and one of the major components of that constructed niche is what we call genetic load. And a major source of genetic load is vaccines. I am not an anti-vaxxer, okay? I love vaccines. Vaccines are the reason that I'm able to go into a lot of very interesting parts of the world and not die, okay? But there is an unintended negative consequence of vaccination, and that is that when we vaccinate, we don't target just the genetically resistant hosts. We target everybody. We vaccinate everybody, including these hosts, the hosts in this part of the host population, that normally would have died from the disease. They would have gotten sick and not recovered. But because they've been vaccinated, now this is genetic load. This is what the population looks like now. The human population is now made up of a lot of people who are not genetically disease resistant, and they're not producing children who are genetically disease resistant. They're technologically resistant. If we stopped vaccinating, or if we lost the capacity to vaccinate, it would be a blankety-blank disaster. Now, it turns out this diagram can also be used from the perspective of the pathogen. All right? So now, this is not host susceptibility. This is not human resistance to disease. This is influenza. How do we make the influenza vaccine every year? Well, we guess at what the predominant strain is going to be, and we make a vaccine that targets that. Now, we do that for a number of years and a number of years, and we end up with influenza that looks like that genetically. And one of the things that happens when you do move it from here to here is now you can't predict so well. Now it really is a crapshoot. You just, throw a dart at the board and decide what strain you're going to make the vaccine after. And we've done it to ourselves. And the road to hell is paved with what? Okay. We interfere with selection for resistance. That's part of our technological niche. We create scenarios in which pathogens and hosts are asked to adapt to pharmaceuticals rather than to each other. genetically non-resistant hosts, and rare pathogen genotypes are maintained. This turns out to be very profitable for pharmaceutical companies in the short term, but in the long run, it's a disaster. It's not sustainable. So the planet is actually what we've referred to as an evolutionary minefield, or a minefield of evolutionary accidents waiting to happen. And I only put this up not for the usual academic ego, but just to point out that we published that in 11 years ago. So a lot of the things that I'm telling you about are things that my colleagues and I have been saying for between 11 and 25 years. And they were true then, they're still true now. So if there was ever a time to think outside the box, this is it. Because climate change is accelerating, so time is critical, action is critical. We're past some tipping points and already into what Satmari calls a second-order world. That is, not only are things changing, but the rate of change is accelerating. That's one of the reasons that countries that are making guidelines and, okay, they're drawing lines in the sand for climate change, and almost as soon as they announce the guideline, we're past it. We can't afford business as usual. Now, what's at risk? Okay, now, as an evolutionary biologist and a conservation biologist and all this is sort of heresy. But I'm going to tell you, the biosphere is not at risk. Because the biosphere is a whole lot more robust than we are. So the biosphere is 20 million species, we're one. The biosphere is made up, 90% of the biosphere is microbes that have been around for 3 billion years. They've seen it all. They're really tough. Evolution is, as Maynard Smith and Satmari said in their 1995 book, a system of indefinite variation. There's always going to be enough capacity there. You'd have to wipe the entire planet. You have to turn the entire planet into a cinder to stop evolution. And I'm also going to say that Homo sapiens as a species is not at risk. And the reason for that is because there are so many of us, and we're everywhere. Some populations of humans, no matter what we do, some populations of humans are going to survive. I know a bunch of people that live up tributaries of the Amazon who have no idea what the internet is, but they know how to hunt and fish. They're going to survive. What I'm going to suggest is that what's really at risk is us. Is electricity, the internet, clean water, modern medicine, air conditioning, automobiles, airplanes, solar panels. And you go, but wait a minute, that can't be true. I mean, this is us. Aren't we in charge? Aren't we in control of this planet? No. We actually live in a bubble. False hope and denial. Denial is very strong. Just think of the story of Cain and Abel, right? Now, the story of Cain and Abel is fundamentally a story about the power of psychological denial, okay? Cain's talking to God. I mean, this is capital G God, omniscient, omnipotent, knows all, sees all, and Cain says, brother? What brother? Oh, the dead one over there. I didn't notice. That's psychological denial. The Talmudic scholars knew 5,000 years ago that denial was a really important part of us. And so what I'm going to suggest is that the human beings who feel most protected from the emerging disease crisis may in fact be the most vulnerable. And after the presentations that have come before me, this is not going to be a surprise to any of you. Okay? Cities. There are at least five reasons why highly technological cities are unusually vulnerable to emerging disease. One is that they produce nothing. They require a constant inflow and outflow of goods and materials. Okay? We know this from New Orleans and Hurricane Katrina. You shut off the supply lines, you bring the power system down, and within 72 hours, city people are killing each other for food. Cities have high population densities, which means that infected people will come into contact with uninfected people more often than in rural areas. There is extreme division of labor with extreme interdependency in cities, which means that you don't have to have a disease that gets into a city that kills people. You just have to have a lot of sick people. And suddenly, the person who's in charge of the computer system at the bank is sick, and her backup is sick, and so the bank's not open today. Check again tomorrow. And those people may not die, but maybe they're going to be sick for a week or two, or 3 or 4. And they're also tying up healthcare workers. Cities provide safe environments for species of zoonotic significance. Earlier this year, in September, a raccoon jumped onto a truck in rural Ontario, and the driver drove that truck into Toronto where the raccoon jumped off, and within a week, there was a massive outbreak of rabies inside the city of Toronto. Cities are really good at providing safe havens for reservoirs of disease. That raccoon would have died alone and unlamented out in the countryside and would never have infected anything else. And finally, the real Achilles heel of most modern cities is that their unsustainably high lifestyle is based on a subculture that is undereducated, undernourished, and essentially invisible to social services, especially public health services. And those people handle our food and our garbage. So, 2 hard landing scenarios. We've been working on this for a year. The first is that we have a pandemic in a rural area, a food-producing area. And this knocks down a bunch of people in the rural areas. But it also kills the cities. If food doesn't come in from the rural areas into the cities die. And I'm sorry, but the vast majority of my undergraduates at the University of Toronto would not know how to leave the city and find food. They would just sit in the city. They would kill each other for the food supplies that were still in the grocery stores, and when they ran out, they would just sit and starve to death. Or we could have a pandemic that occurs in an urban area. Wipes out a bunch of people in the city. The rural areas survive, but because the technological infrastructure is maintained in the city, technological infrastructure crashes. So the rural areas survive, but they survive as non-technological agrarian societies. So those are 2 hard landing scenarios. And we worked for a long time to come up with the possibility of a soft landing. Okay? And this is the one we've come up with. Hopefully there are others. But what we're investigating now is the possibility that a network of cooperating countries, and this is not a rich versus poor kind of thing, haves and have-nots. So it's not going to be that way. What we're going to have is a network of cooperating countries that include producers and consumers, technological hubs and food-producing hubs that are willing to share information, share resources with each other for a common good, which is survival. And the reason for that, the reason we're worried about this is because what we would love to see, I love the internet. I love being able to come to Singapore. I love the fact that when I was 21 years old, there was a doctor who could take out my infected appendix and I didn't die. I'm really happy about that. I got an extra 45 years of life out of that. So we don't want it to go away, in fact. And I have children and grandchildren, and I don't want my grandchildren, my great-grandchildren to ask what kind of fish you catch with an internet. And the only way we're going to be able to maintain this level of technology is if we get the human population down. So everything I'm talking about now is all about buying time to reduce the human population. As an evolutionary biologist, what I believe is that the human population is it's too big and it's going to be adjusted. The question is, are we going to have anything to do with that? Are we going to have a say in how that happens? Because we're afraid that if it happens too drastically, we could lose our technological infrastructure. That's what we think is really at risk. So, be afraid, be very afraid, but don't panic because we have a plan. Now, this plan is not based on the notion that, oh, we only have X amount of dollars for health care, so if we're going to fund your suggestions that I'm about to give you, we have to take it away from something else. You have to reject that premise. Because I've already told you, we cannot stop doing what we're doing. We can't stop making vaccines. We can't stop vaccinating people. So this is, the bad news, wait for it, is this is going to cost money. There's not a lot of time. I mean, these are some dates that have been mentioned during this week so far, during these last 2 days. We can't reverse climate change. I'm sorry, I love Barack Obama, but he's delusional, like all city people. Oh, technology is going to, it's like when the British Petroleum oil operation blew up in the Gulf of Mexico. Barack Obama's first reaction was, plug the hole. It's like, call the plumber, right? It's like, no, it doesn't actually work that way. It's not a city. We can't stop it, we can't reverse it, but we can prepare for what's coming at us. We can't stop emerging diseases. But we can anticipate them. And by anticipating them, we can mitigate their impact. We can buy time while we work on coming up with real systemic solutions, like there are too many people on this planet. We can't medicate, vaccinate, and eradicate our way out of the crisis. Now, this medicate, vaccinate, and eradicate, that's what modern medical practice is based on. Medicate the sick people, vaccinate the youngsters, and then eradicate pieces of biodiversity that are associated with transmission of the pathogen. We've been doing that for a long time, not working. But we can reduce the damage and buy time. We have to be proactive, and that means we have to replace do no harm with the precautionary principle. The precautionary principle from biology says incomplete knowledge is no reason not to do the right thing. So, one of the things we have to do is cooperate. And cooperation is used in two different ways in the literature right now. One of them is this idea of let's cooperate and I'm sure we'll find some solution. That's a good way to generate money for conferences and edited volumes. The alternative is we've got a solution that will work, but we have to cooperate to make it happen. That's a much more powerful, that's an action plan. Okay? Now, in the case of the Stockholm paradigm, here are a group of people. These are the people who have been most involved, most recently, in producing this particular piece of science. And of course, they all have students and colleagues and students and colleagues. So in fact, behind all of these people is an enormous network of scientists and a lot of publications. The word adaptation is thrown around now. Finally, after 7 years in office, finally somebody convinced President Obama that he should start talking about adapting to climate change, which was an improvement because that's at least not delusional. Unfortunately, adaptation for most non-biologists now means let's respond to the crisis after it's emerged faster. Not, let's anticipate what's coming at us and adopt measures to either stop it or mitigate its impact before it happens. And again, one of these is not helpful and one of them potentially is. Now, we've developed what we call the DAMA protocol, which stands for Document, Assess, Monitor, and Act. This is the program for trying to anticipate to mitigate. Okay? Document. You can't plan for something if you don't know it's there. There's no management plan for a species whose existence you're unaware of. Know your enemy. Here's a dirty little secret from biology. We don't know anything. 90% of the species on this planet are parasites, pathogens of some sort or another. We've discovered and named about 10% of them. That means, for example, that 90% of the potential pathogens that are in Singapore right now, we don't know about. Because it's not, and I'm not just picking on Singapore, I happen to be here. You can say that about any place on the planet. The inventory that I did in Costa Rica was the first time in history that anybody attempted to document all of the parasites in all of the vertebrates in one place on the planet. And that's still the only place where we've got those data. So we have to change this. I mean, you can't anticipate things if you don't know they're there. So step number one is know your enemy. Now, the interesting thing about this is that taxonomists, the people who know how to document, are actually trained to expect the unexpected. In fact, we go out looking for that. It's one of the reasons I became a tropical biologist, because I knew every time I went into the jungle, I would find things that nobody else had ever seen before. And I was trained to recognize them when I found them. There's a microbe, it's actually a bacterium, not a virus, called Borrelia. It causes a disease called Lyme disease. And for many, many, many years in the United States, there was a lot of controversy about Lyme disease in the United States. Most doctors felt that it only occurred in New England, in the northeastern part of the United States, and had one particular set of symptoms. And there was another group of doctors that said, no, it's much more widely distributed than that, and it actually doesn't always have those symptoms. Well, it turns out that we now know that that mess that led to a lot of undiagnosed people becoming very, very ill was the result of bad taxonomy. There are actually 2 species of Borrelia causing Lyme disease in North America, one of which is in the Northeast, one of which is more widely distributed, and they each have slightly different symptomology. And that's just bad taxonomy. So what do we need to implement that? We need taxonomists and parataxonomists. We need inventories and rapid identifications. And that means we need lots of new generation sequencing stuff. We need reference collections and databases because we need to share this information. All right, assess means basically threat assessment. Now, we start doing these inventories, we're going to find an enormous amount of stuff, not all of which is going to be a threat. Most of the microbes in the soil here actually are helping the trees grow and helping the grass grow. So how do we triage? How do we decide of all these thousands of things that we're documenting, how many of them, which one should we focus on? Well, it turns out that one of the best ways to make an educated guess is to put everything new that you've found into an evolutionary framework. Ask what its closest relatives are. You get a bacterium you've never seen before, you put it in a phylogenetic analysis, it turns out to be closely related to something that causes disease, then you know to focus on it. If it's closely related to something that helps macadamia trees grow, you leave it alone. You don't waste time on it because it's not a problem. Once you've got the species that you've been documenting into this phylogenetic framework and you've identified the potential threats, the ones that you really want to focus on, you can then make educated guesses about the transmission dynamics, because more often than not, the pathogen's transmission dynamics are going to be very similar, if not identical, to its closest relatives. So for example, I'm going to say malaria. How many of you just thought mosquitoes? Okay, virtually everybody. But I didn't tell you which of the 4 species of malaria I was talking about that infect humans. I didn't tell you what part of the world. But the reality is that no matter which of those species of malaria I'm talking about, no matter what part of the world, they're all transmitted by Anopheline mosquitoes. So we take advantage of this evolutionary conservatism in specialized transmission dynamics to be able to make educated guesses about what's going on. And once we've got that, then we can start to do something about mitigating the impact. Because then we will know the essential pieces of natural history, or have a good idea about them, that we can begin doing something. The species that our triage tells us are important are things that we would then go back and do really intensive monitoring for, because those are the ones where we really need to find those rare genotypes that could potentially be the really bizarre pathogenic things, or the things that would get into an unusual host. And once we've got that demographic information, there are now mathematical models that we've developed that we can put the demographic information into. We can look at profiles of matches between the host and the pathogen genotypes to understand whether that pathogen has recently gotten into the host or whether it's been there for a long time. But for this, we need population geneticists, population ecologists, phylogeographers, and modeling specialists, and specialists in surveillance techniques. We also need community involvement. It's essential. We need regular observations by citizen scientists relevant to changes in local ecosystems that could enhance transmission dynamics of the targeted species. And I have a friend, some of you may know Alicia Guerrero from Washington, D.C. Vector Analytica is a company that she's the president of. This is a system for community-based disease mitigation by citizen scientists. All you need to have is people with a cell phone and about a grade 3 education. You tell them what to look for, they see it, they call in, somebody at the call center says, you found water sitting in an old tire. That's where tiger mosquitoes like to breed. Empty that water now. Much cheaper than waiting for a dengue outbreak in the village. Boots on the ground to eyes in the sky. So this has to be scalable up. This has to be not only coordinated in cooperation among countries, but you have to be able to go from the activities of citizen scientists to these large-scale global surveillance, climate change surveillance satellites up there. Now, acting, that is doing something about this. Once we've found out, what's a possible problem, what's going on with it, what do we do about it? We don't just watch it happen. You have to get the word out to local people to tell them that there is a potential risk in their neighborhood, in their backyard, in their local forest. And to do that, you have to be able to teach them what to do. You have to mobilize the relevant agencies, help agencies, aid agencies, governmental and NGO, to help people with that. So that means that in order to act, we need specialists in public activism, public outreach, and education and training. Education is absolutely essential. Everybody has to be educated to make a contribution, all the way from citizen scientists to policymakers. And people have touched on both of those topics, and the issue in my experience, it's actually easier to teach somebody in a rural village in the Amazon than it is to teach a politician. Mostly because the politicians have more complicated lives and more different things going on in their lives. Everybody has to contribute something. So we have to integrate all of these human activities on multiple scales and across disciplines, everything from citizen scientists to actual professional scientists and government policymakers. Now here's another bit of bad news. This is a lifestyle change. This is not cheap, it's not easy, and it's permanent. If we either do this right or we don't do it at all. But if we do it, we have to understand that this is just the way societies have to behave on a permanent basis with permanent funding, at least until we've got human population down to a sustainable size. So here's a bit of a summary of what's going on. So here are the 4 horsemen of the apocalypse. This is all a matter of national security. And interestingly enough, the governmental organizations that have been most proactive about drawing up contingency plans for coping with climate change are military organizations, national militaries. In the United States, the Pentagon spends more money buying information about climate change from the National Research Council than any other government agency, including NOAA and the Environmental Protection Agency. But here's where things fall apart. We know this, okay? But then when we go over here to actions, we go right down there to react. Do no harm. Wait till there's a problem and then throw stuff at it and hope it goes away. Here's all this proactive stuff. We don't do any of that. And up here we have basically, here's the Ferrari that we've built. Down here, there's the gasoline company. We're not getting any gasoline into the Ferrari. So the Ferrari could go 1,000 miles an hour, but only if it has gasoline in the tank. And you're not going to get gasoline in the tank without a lot of buy-in from the public and the government. Talk is cheap. Actions speak louder than words. It's that simple. So as a Swedish friend of mine said at a UNESCO conference one time, think globally, act locally, start now. Unfortunately, he said that 25 years ago. And everybody said, yes, let's drink. No one's to blame, but it's everybody's fault. And we're all being asked the same question. It's what we call the Dirty Harry criterion. Do we feel lucky? Okay, because it's possible that everything I've told you about is crap. There's not going to be any kind of disease crisis. We've seen the worst of it. It's going to go away. We'll be fine. Everything will be cool. And if that happens, the worst thing that could happen is that you would laugh at me for overreacting. And I can live with that. Because the alternative is that my grandchildren get sick and die because you didn't listen to me. Then I get angry. And I'm old, and I'm a field biologist, and I know how to kill things. I got nothing to lose. Now, to go all the way back to those temperature profiles from 10,000 years ago, here's the weird thing. If it turns out that human civilization could only have emerged during a window of time of unusual climate stability, we may not have another chance. So if we lose this, I mean, we know, for example, if we lost all of our technological infrastructure, we could not rebuild technological humanity based on petroleum, because the only petroleum left in the ground requires high technology to get it out. And guess what? We can't make solar panels without petroleum-based high technology right now. So, you know, this is This is some serious blankety-blankety blank. So we might not get a second chance if we screw this one up. We have the ability to save ourselves, but we don't seem to have any interest in doing it, which is really bizarre because we're all taught that self-preservation is such a strong instinct and all this sort of stuff. And that may be true on an individual basis, but it seems that on a collective basis, we're like a really big troop of baboons. We see a threat and we go. And then we run away. And we hope that somebody else gets eaten by the leopard. Hopefully somebody we didn't like. But I think human civilization is a great idea, and I think we should give it more of a chance. And if I sound abrupt and too isolated and too objective and not emotional enough and all that sort of thing, it's because scientists are trained in the same way physicians are trained to have a certain degree of professional detachment. A physician like my father, who could not have emotional detachment, could not actually operate on a seriously injured person without being so upset about the fact that the person was suffering that he couldn't do anything. So you have to be able to go into a different mode where you actually do the operation and then you worry about the fact that the person was really hurting later. And scientists are sort of trained to do that. So I can be very, sort of cold and objective. We need to do this, this, and this. Give us a lot of money and we'll do good things. But it doesn't mean that I don't really care. But it does mean that I'm capable of professional detachment. And as Dorothy Sayers said in her famous novel, Gaudy Night, detachment is not a trait that many people find to be very lovable. And I will finish by explaining the Cassandra Collective. This is another problem. I have a lot of friends who are my age, plus or minus a decade, who have been working like I have. We have been on the long march for 30 years, 35 years, trying to do something about biodiversity and climate change and emerging diseases. And nobody's been paying any attention. And now, in the last year, I've started to see Facebook postings from those people, and they're not postings about the most recent conference they attended. They're postings about being on holiday with their grandchildren and taking that trip with their husbands or wives or their partners that they always wanted to take. And they're not making a big deal out of it. They're not making a public announcement. They're just walking away. And this is expertise and experience that we can't afford to lose. But a growing number of professional biologists with incredible amounts of expertise are saying, you didn't listen, now it's too late. I figure we have about 20 years to go before it all crashes. I have about 20 years of life to go. I'm going to have a party. This is the James Lovelock suggestion. But this is happening. I mean, this is a trend that's not a good trend. Now, those people, a lot of those people could be co-opted to come back and participate if there was a reason to do that. And one of the biggest deficits that we have is what's called the taxonomic impediment. There is no country on this planet, including the United States, that is self-sufficient with respect to taxonomic expertise. If the United States wanted to document everything in its biodiversity, it would be heavily dependent on foreign experts. And every country is in that same boat. Now, the nice thing is that scientists like to cooperate with each other. Taxonomists love this. If somebody calls them up and says, hey, how would you like to come to Finland to look at species that you've only known as museum specimens before, and we're going to let you go out and collect them alive? It's like, I'm there. And we work really cheap. Buy me an airplane ticket, put me in a pension, I'm good. Get me a collecting permit, I'm there. But we're losing that expertise. And we're losing it at an increasing rate at a time when we can't afford to do that. So I hope that there's some hopeful possibility. In other words, having something like the Dhamma Protocol makes me hopeful that we could do something to save ourselves. But as a result of my X number of years in the business, I don't have a lot of optimism about it. And I would love to be proven wrong. So thank you very much for your attention.
Thank you, Daniel, for that very thought-provoking talk. So now's time for questions and discussion. Right, Sasha.
Hi, Daniel. I'm a microbiologist, so I understand a little bit what you're saying here. I think the major, one point is, it's a remark, and then I have a few questions. But one point is, this has nothing to do with, primarily not with climate change. It has to do with the increase of population density, creation of new niches, the way we act as a human society, and building new environments, and then every new niche is almost a potential danger of nice things, but it's also a potential danger that something can go wrong.
Right.
And we know in the meantime that the biology has mechanism. You have a plasticity in the cell itself, but you have all these islands which are around, like pathogenic island and all kinds of islands we know, they are almost floating free. So if you find the right niche, it will come. So that's kind of the remark. A second remark.
Well, let me answer the first one, and then we'll go on, because I don't. The rest of these guys are much better at holding multiple questions in their minds, but my hard disk is a 1951 model, and it's heavily fragmented.
So they still have a Winchester.
So as it turns out, let's suppose you're correct. Yeah. Okay, that despite the fact that there's global climate change ongoing, and we know that one of the impacts of global climate change has always been an increase in emerging diseases, let's assume that that's not affecting human beings. Let's assume that it's just overpopulation. That's okay. That's fine with me. Yeah. It doesn't really matter, just as it doesn't matter whether automobiles are causing this or whether what we're seeing now is not the result of automobiles, it's the result of the beginnings of the Industrial Revolution, and we haven't yet seen the full impact of automobiles. Or it doesn't have anything to do with automobiles at all. I don't care.
My point
because
is only,
it's happening. What are we going to do about it?
We should not concentrate. We should not use an argument which may or may not contribute, but it's certainly not the trigger of it. So that's the first thing. The second thing. I mean,
that's an assertion.
The second thing is, I like your almost last remark you said, because what we really have to deal with, you showed this nice system. This system works if we know what we have to look for.
Right.
However, I think the dangerous part is we don't, if we have to look for something we do not know. And if you look what happens if disease outbreaks take place, it is not the younger people who have all the knowledge but little experience. It's very often the old guys who go to Hawaii with their kids. They of a sudden see that something is not as it should be. And I think for your remark that actually we have to get the older guys back, not because they are better, but they have seen more.
No, we have to get them back so they can train a new generation. I'm sorry, I didn't make that clear. No, the reason to get all the old people back is to train the next generation of people to go on.
Yeah, but also because you have the experience. You have also the experience. I think this experience
but once upon
is
a
not
time,
something which you, not because I have gray hair I say that, but I think it's an important thing.
No, I understand what you're saying. Once upon a time I had no experience either. But I did have training and aptitude, and I had a mentor with me. Okay? So the reality is everybody like me once upon a time didn't have any experience. Yeah, but that's not an argument for saying we shouldn't do this.
No, I think we are on the same page here. So we don't have to argue. We agree. So okay. But the point is, my question is now, all the things we have said, is at the end of the day, you should be able, not only going into taxonomy, but you have to really go down to the genomics of the system. Do we have certain mechanisms and traits when new diseases or old diseases pop up in new places? Do we know what the molecular mechanism is of that, the molecular mechanism of the adaptation of the pathogen to the new environment? Do we have a clue of that?
Well, okay, there are two questions here. One is, do we know, and the other is, do we have a clue? Okay, yes, we do have a clue. Okay, we know how to look for the signature. Okay, and that's the mathematical modeling we've been doing in the last couple of years has gotten us to those profiles. The more interesting question and the more frustrating question is, do we know the actual trigger in each individual case? And even for that 10% of the pathogens that we've documented, we don't know the actual trigger for very many of them. I mean, that's a problem. So we don't know what triggers disease in some cases, and in other cases, we don't know what the pathogen's interaction with its host is that leads two closely related viruses to produce really different diseases. Okay, because Zika, I'm really surprised. I've seen nobody discuss this analogy between Zika and rubella. Now, for most of you, I look out there, most of you are too young to know what that was. But we have measles and mumps and rubella. They're closely related bugs. Now, two of them produce severe, relatively severe disease in children and some young adults. One of them produces only a very mild set of symptoms, sometimes not more than just a rash, but it has devastating impacts on developing fetuses. The same way with dengue and yellow fever and Zika. 85% of infected adults are not symptomatic for Zika. Dengue is called breakbone fever because your muscles contract so much when you're sick that it feels like your bones are breaking. But you get over dengue, if you were pregnant, it's not a problem. Your fetus is fine. You feel like hell, but your fetus is fine. Zika is sort of the opposite thing. And many of you may have heard that there's a big controversy. Oh, microcephaly. No, it's a tiny proportion. It's not such a big deal. Well, it turns out now that what the Brazilians are finding, because they're doing the follow-up, is it turns out that, yes, only a tiny fraction of Zika babies are microcephalic. But all of them have some developmental deficit. There are hearing problems, there are vision problems, there are cognitive problems, and in the outbreak in Colombia that's happening right now, in infected adults, there is a spike in an outbreak of an autoimmune disease called Guillain-Barré syndrome. So we really don't know the full extent of all the things that can happen with this, and we don't know what the damn triggers are. And that's, now the fact of the matter is, that's an important thing to understand for treatment, right? But you know what? If I can teach a bunch of people how to avoid getting bitten by mosquitoes, I'm probably limit exposure a lot more than somebody looking at the genomics of the pathogen can do. That's why we can't stop doing this extremely important work in figuring out the actual molecular triggers. We can't stop doing that. But it's not enough, partly because it takes time. I mean, even if you have unlimited resources, it still takes time to figure this out, then develop a vaccine, blah, blah, blah. The rubella outbreak, okay, British scientists knew in 1947 that rubella was associated with birth defects in pregnant women. It wasn't until there was an outbreak of rubella in the United States in 1962 that there was any kind of social pressure to develop a vaccine, and that vaccine wasn't developed until 1969. Okay, now, yes, we can go faster these days, but not that much faster. Some of you may know that there is a massive, essentially out of control yellow fever outbreak in Africa right now. Emergency supplies of yellow fever vaccine have been exhausted. 2 faculty members at Georgetown Medical School published an article in June in the Journal of the American Medical Association saying it's going to take a year to gear up new vaccine supplies. Yellow fever could be global by that time. Because there's a funny thing about yellow fever vaccine. It has to be grown on chicken egg albumin. So before you can start making new yellow fever vaccine, you've got to create a whole bunch of chicken farms. Get them into high production, then start inoculating them, then begin harvesting what you need to create the vaccine. It just simply takes time. And the reality is that if there actually is an emerging disease problem, then we need to do something to either speed up that process and make it cheaper, or we need to do something else in addition that actually mitigates the impact. So it keeps people from being exposed as often. Well, people and livestock and crops. I mean, like I said, you know, we get back into, the examples turn out to be a couple of human examples. But there is a rust fungus right now that's infecting wheat crops in Africa and the Middle East that does not respond to any known fungicide. And there's a possibility that within the next 5 to 10 years, we could lose the entire wheat crop of the world. There is something called blue tongue virus that was eradicated from Europe. Now it's back. It's currently killing cattle in France and sheep in Slovakia. And each one of these things costs money. Each one of these things, if we were going to deal with each one of these with a vaccine, time and money, time and money, time and money. And the only reason blue tongue virus reemerged in Europe was because nobody was paying any attention. It's gone. You know, it's like when the World Health Organization has a press conference and says, Ebola has been eradicated from Nigeria. No, it hasn't. It's just not infecting human beings in Nigeria right now. It hasn't been eradicated. And when the World Health Organization says, oh, Ebola is in fruit bats, they know that's not true. The virus has never been taken from fruit bats. Some fruit bats have the antibodies for Ebola. It means they've been exposed. Doesn't necessarily mean they've been infected. We know that in the Congo, there are cases of chimpanzees and gorillas and duikers, a kind of antelope, that have been dying from Ebola. And that was documented in 2004. Now, what's the commonality in diet and exposure and transmission between chimpanzees and gorillas and duikers? You know, if I had to make a guess as a parasitologist, I would say that they're being bitten by the same insect, and that Ebola is actually may very well be an insect-transmitted virus. But the reality is we don't know. We don't know what the distribution of that virus is. We don't know what its geographic variation is. We don't know any of the basic biological questions that most of us would say we need to know. Because we're too busy putting on our spacesuits and going and treating these poor people who are bleeding out in front of our eyes. And what I would like to do is to figure out where the damn virus is and then say, that virus is up in the top of the trees. Don't go up into the trees. And then people would stop dying. And I think that a lot of the disease issues can be, the costs can be mitigated. We can buy time by doing that sort of thing. And I know I've wandered far away from your original question, but the reality is that we don't know. We don't know. And right now, new diseases are cropping up before we figure out those kinds of data for the ones we already knew about. So I would just, I think those are incredibly interesting questions to investigate, and I hope we have the time to get to them.
Thank you very much for the very rich content. So I know nothing about all these pathogens and whatnots. So when Zika, when I first heard about Zika in Brazil, because of I'm an Olympic fan, so I did some reading. Well, it's not about eradication of Zika, but there was a so-called laboratory that trying to do something. So their approach is to mutate the male and female mosquito and make them reproduce. And when they reproduce, they say, because of the mutation, the offspring will die very fast. So this is one way they think that they can, through time, over time, how long, I don't know, they didn't say, that they can at least minimize the species. So my question to you, I guess you know what I want to ask, is this valid? They say, they claim that they have some success and they are continuing even at this moment. So I'd like to hear your view on this. So the other small question I have is very interesting because just now you mentioned about BP, about the oil spill. About 2 weeks ago, in fact, actually I witnessed one occasion in London this summer, but 2 weeks ago there was a huge article in Financial Times, London, talking about the protests of BP sponsoring the Tate Modern. And the thing became so huge that they disagree and they want this kind of sponsorship to stop immediately because they don't want to be contaminated with the brand. And I would like to hear your view. Thank you.
Okay, well, I'll answer the second question first because this is just a personal reaction, and that is ideological purity is like saying, stop or I'll shoot. Okay? I mean, the reality is that if people are unwilling to work together for a common good, then we're all going to die. I mean, that's the bottom line. Now, with regards to your first question, this issue of releasing sterile mosquitoes as a form of biological control is very interesting. And in general, my attitude is that anything we can do that helps is worthwhile, is worth doing. My concern about the program of introducing sterile mosquitoes into the environment is twofold. Okay, and the first is there is what we call the Cunningham effect, or it's a priority effect. And it basically means if you've got 2 billion mosquitoes and you release 100,000 mosquitoes into that population, they're going to make no impact. They're going to be swamped out by what's already there. Okay. So that's one consideration is how much money does it cost to make these mosquitoes and how many of them do you actually have to release into the environment to have a significant impact. The other problem is a problem specifically to the idea of creating sterile male mosquitoes is the following. If you want to make a human male sterile, what do? You take away their testicles. Okay? How do female mosquitoes find male mosquitoes? Something called pheromones, which are produced by, male reproductive organs. Those sterile males are not putting out the chemical signal that would lead female mosquitoes to think that they were mates. So one of the things that may not have been taken into consideration is that mosquitoes are not just bags of genes. They're actually organisms with things like behaviors and ecological preferences and things like that. And then as far as some of the actual manipulations that they're doing, genomic manipulations that they're doing, it's not necessarily true that the offspring of sterile or relatively infertile mosquitoes would themselves be infertile. Okay, genomes are incredibly interesting systems of their own, with a lot of their own rules and a lot of self-repair capabilities. And there are a number of cases in the biological control literature of situations in which a deleterious gene, for example, just gets recombined out. And so after a few generations, the engineered organisms just aren't there anymore. The gene that was causing whatever effect they wanted, it's not there anymore. And of course, we don't know. Many of these things are things we wouldn't know until we had tried for some period of time. So, of course, anything that's possibly of benefit, we should try. But we should never expect any one thing to solve the problem. And with respect to Zika, all they're doing is with the engineered mosquito, they're just doing it with one species of mosquito. And filoviruses, like Zika and yellow fever and dengue, it's a myth that they only use one mosquito. In fact, it's a myth that they only use mosquitoes. In Central Africa, where you have seasonal ecosystems where there are extended dry periods, the yellow fever virus survives the dry period. When the mosquitoes aren't around because there's no water, what's the virus do? It lives in ticks. And Zika is sexually transmitted, like Ebola, HIV. So no one thing is likely to solve the problem. But it's like, there's a story of a young person coming to Mahatma Gandhi saying, "Master, what should I do?" And Gandhi said, "Nothing you do will make any difference. But it's very important that you do it." And that's, we have to try everything because what we're trying to do is buy time.
Daniel, thank you for a very thought-provoking speech. Something that catches me while you're saying is in regards to population, human population, and you were saying that we have to reduce our population. We are roughly we just passed about 7 billion, and we will be touching about 9 billion in about 10, 15 years' time. So my question to you is that given that we are still on the rising trend, and you are saying that we have to reduce human population, could you elaborate more? Because I didn't see anything that was put up in regards to reducing human population. And because, and let me add on one more point, is that for any government, the moment they see their population is aging, they will be putting all measures to bring back their population. For example, in Singapore, we are classic, but we are not alone. China, because of their one-child policy, and they see that in another 10, 15 years, they're going to have aging population. They have already relaxed the one-child policy, allowing for 2, and they say, well, we can consider for 3, because not all of their population is interested in having more children, especially the urban. So my question to you is, how do you reduce human population?
Well, My experience in Costa Rica is my direct experience with that. There are about 140 Costa Rican employees of the conservation area where I worked. Most of them are women. They are making salaries that are higher than the median income for the country, which is already the highest in Latin America. So these are people who are bringing in a substantial second income into the family. And about 5 years ago, we made a chart. Put all the names of these people, and here we said, how many brothers and sisters do you have? How many children do you have? 11, 2, 6, 1, 5, 1, 4, 2, 8, 0. One generation, educational opportunities and economic opportunities for women. Women control the reproductive output. Every country on this planet that has its population under control has substantial economic and educational opportunities for its women. That's how to reduce it. Now, that's a scientific answer. You know, try to sell that to every single culture and religion on this planet. That's the roadblock to that. But that's the way to do it. That's the humane way to. If you want disease to do it, then don't stop vaccinating. Don't do anything. The next time somebody says, I've got Ebola in my village, you just say, sorry. That'll do it. Wait for 50 years till the soils are depleted and people are starving to death. There are lots of ways that if we do nothing, the human population is going to be adjusted. But if we want to have a soft landing, if we want human population to either, because we actually don't know, it seems that the carrying capacity for humans is much higher than Paul Ehrlich thought in the 1960s. But we don't know what it is. And because it's a nonlinear system, we're not going to see a gradual approach to the carrying capacity. A carrying capacity is kind of like an airplane flying along and the wings are vibrating and every so often one of the bolts flies off the wing. But the airplane's still fine. Then another bolt flies off and the airplane's still fine. And then finally, one too many bolts flies out and the airplane suddenly goes from 100% to 0%. And if that's the case, if that's what we're looking at, then we have to be very careful. And we have to think of carrying capacity not as an absolute quantity, but the number of human beings on this planet that we think we have a chance of providing a high quality of life for. You know, if we add 3 billion more starving people, that's, you know, just to make a point about maximum carrying capacity, that's probably not something that I would endorse, okay? So part of it is a voluntary, saying, we think there are too many people on this planet to feed and house and take care of comfortably. And it may not be the absolute carrying capacity. Nonetheless, it seems to be unsustainable economically. The only way we're sustaining this high population now is there are a lot of poor people. So there's, you know, in a sense, there are two different answers. You know, one of which is kind of this scientific answer, and at what point do we actually asymptote? And the other is, would we like to try to slow things down now? But as far as the policy for doing that, the only policy we know right now that actually is effective in controlling human population is education and economic opportunities for women. And you know, it's a deceptively easy sounding thing to say.
Any more questions? Very last one. Thank you.
Well, Daniel, thank you very much. You know, very enlightening. One thing about it, because I want to confine to the simplest one. Well, you cover a lot of Cassandra crossing, to multiple of them. Now, one element that when you say the collaboration between individual, layperson, in a civic engagement with a specialist, but there's no such system embedded currently right now, globally. But do you have some framework that you think already implemented, that you think that it is good to look into, and would you care to elaborate on that? Thanks a lot.
Yeah, that's actually a really good point. Partly it's a good point because I actually have an answer. Two levels, okay? The first answer is that we have field tested that in particular with these inventory projects in Costa Rica. Now, the reason I got involved with the project in Costa Rica was because the science was going to be interesting, but the conservation area system in Costa Rica is based on what we call the use it or lose it principle, that sustainable use of biodiversity is better than building a fence around it. And that if you can show local people that their own socioeconomic status, and especially that of their children, benefits from sustainable use of the biodiversity in the conservation area, then the local people will preserve their biodiversity. And so that conservation area is the only World Heritage biodiversity site in the world that has no fences, and no guards, and no gates. The first few years I was there, before all the people in the villages around the margin got to know me, I would have people stop me and demand to see my collecting permit. This is some poor campesino saying, wait a minute, show me your collecting permit. This is great. This is community buy-in. We also went into the villages and found people who had unusual aptitude for their local diversity. That's where we got the parataxonomists. And we would do things like we would give them a cigar box full of insects and tell them to classify them, or a plant press with a whole bunch of plants and say, classify these things. It's unbelievable. I mean, most people, not very good at it, but in almost every village, there would be one person who would be doing it at the same level that a Smithsonian taxonomist curator would be able to do it. So there's a lot of capacity there that's underdeveloped. So then what you have to do is you have to have people like me who are interested in going into another country, and as a trade-off for being able to do my science, I train what we call capacity building. I train the local people. And then when I go away, they don't need me anymore. I mean, you know, they might like to have me come back from time to time, but I'm not essential. So we can do it. We know how to do it. We have done it. There is this concept of parataxonomists and paraecologists, and it works. Now, at the next level of that, I would just say that I've just written a white paper on this for the Hungarian government, and next October, we're hoping to have a workshop in Község about trying to implement aspects of the Dhamma protocol at different levels. One would be a network of communities within Hungary sharing information. Another is cross-border collaboration between Ukrainian and Hungarian scientists. And then at the next level, a tie-in between what's happening in Hungary with Costa Rica and with South Africa. So the idea is to try to get this on different scales and to see if we can actually scale this up so that we would basically train parataxonomists in Hungary, and the parataxonomists in Hungary would basically be doing the same thing that the parataxonomists in Costa Rica were doing, just in different places. And as a consequence, if you're, say, you know, an insect curator at the Natural History Museum in London, you could go to Costa Rica or go to Hungary and know that there would be a well-trained paraprofessional completely familiar with the local flora and fauna that you could work with. That's going to save time and money, right? So we know it's worked with what you would call the pilot study in Costa Rica that's been developed. That system's been developed over about 30 years. Now we're going to hope to get funding to scale that up and to show that it could work. It doesn't necessarily only have to work in a tropical developing country. It could also work in Europe. I also say, I just realized something, a third element of controlling human population. The networking, cooperating nations are going to survive. The ones that opt for isolationism, okay? The United States decides to build a big fence around itself. Okay, Edgar Allan Poe, you know where I'm going with this. Edgar Allan Poe, an American writer, wrote a short story in 1842 called The Masque of the Red Death. Where have we heard that before? And it was all about a mythical city-state in Italy somewhere. So the Red Death was actually the bubonic plague. And the plague broke out in the rural areas and started coming into the city. So all the rich people got a whole bunch of food together and wine and musicians, and they went into the castle and they closed the doors and they said, we're not coming out until all the poor people die. And 6 months later, the poor people opened up the castle and everybody inside's dead. Well, you know, in the contingency plans that we're drawing up, we're not assuming that the United States or Russia or China are going to cooperate. If they do, that's fine. If they don't, then they're betting that they can be self-sufficient, that there either will not be a crisis or they can take care of it all by themselves. Okay, that's fine. But my suspicion is that no country is completely self-sufficient. And I'm an American. I mean, I'm not saying that I would really enjoy it if my country died. But as Voltaire said, there's a certain inevitability about inaction, right? You don't do anything, something will happen anyway.
Okay, so
Thank you.
thank you very much, Daniel, and you're showing your appreciation.